Today, in the displacement article of sound, we have shown the figure for sample pendulum. The displacement can be represented by a mathematical function of time. In case of periodic motion, this function is periods in time. One of the simplest periodic function is given by f t बराबर a cos omega t. Now t बराबर 2 pi by omega is equal to time period. The function f t is periods with t capital. F t बराबर f t plus t. The same result is obviously correct if we consider a sine function f t बराबर a sin omega t. इसलिए एफ टी बराबर a sin omega t plus b cos omega t. It is also a periodic function. Taking a बराबर d cos phi and b बराबर d sin phi, we can get f t बराबर d sin omega t plus phi. Here d and phi are constant given by d बराबर root over a square plus b square and phi बराबर tan inverse b by a. Thus, any periodic function can be expressed as a interposition of the sine and cosine function of different time periods with suitable coefficient. Sample harmonic motion. In the figure given, the position minus a to a from the mean position is directed towards a particle which vibrating back and forth about the origin of axis between limits plus and minus a. Let us consider a particle vibrating back and forth about the origin of an axis between the limits plus a and minus a. Its speed is maximum when it is at origin and zero when it is at plus minus a. The time t is chosen to be 0 when the particles at plus a and it is assumed to return to 0 at t बराबर t. A graph of x as a function of time for the motion represented by x बराबर a cos omega t plus phi, where a, w and phi are constants. Thus, x बराबर a cos omega t plus phi, where x is the displacement, a is the amplitude, omega is the angular frequency, and phi is the phase constant. The motion represented by equation is called simple harmonic motion. A is the amplitude of motion, omega t plus phi is the phase of the motion, phi is the phase constant of phase angle. Now x बराबर a cos omega t for phi is equal to 0 as shown in the figure. X बराबर a cos omega t for phi is equal to 0, इसलिए x बराबर a cos omega t plus t, omega t plus t बराबर omega t plus 2 pi, because it is added by 2 pi, increased by 2 pi, it is increased by 2 pi. So omega t बराबर 2 pi, इसलिए t बराबर 2p बटा omega और omega बराबर 2 pi by t. SI unit of angular frequency is radian per second. Simple harmonic motion and uniform circular motion as shown in the figure 1. The radius is shown by a and displacement is shown by x t and phase angle is shown by omega t plus phi. Thus, we can get as a function x t बराबर a cos omega t plus phi as a displacement. Now velocity and acceleration in simple harmonic motion, v बराबर omega a and vt बराबर minus omega a sin omega t plus phi और vt बराबर dxt by dt for instantaneous velocity of the particle in motion. For the acceleration shown in the figure, it is magnitude of radial acceleration of p is omega square a, so a t बराबर minus omega square a cos omega t plus phi, इसलिए बराबर minus omega square x t, इसलिए बराबर a बराबर dvt by dt. It is instantaneous acceleration as shown in the figure for displacement, the graph a, for velocity v and for acceleration c. Thus, it is the representation of the graph between x and t, v and t, a and t, as shown in the figure. Now the first law. For sample harmonic motion, ft बराबर ma बराबर माइनस m ओमेगा स्क्वायर xt और ft बराबर माइनस kx where k बराबर m ओमेगा स्क्वायर और ओमेगा बराबर रूट ओवर k by m. Thus force is proportional to the displacement and directed to in an opposite direction. Since force F is proportional to x rather than to be to another power of x, which such a system is referred to as linear harmonic oscillator.